Hello guys, in this video we'll learn about some key variables in describing an object's motion. Variables in motion. Now first let's think about why do we want to describe an object? So we know an object, let's say at the beginning it's here, right? And then after some time, in a common language sense, after some time it's here, then people would be interested in knowing the exact location of this position and that position. Let me call this initial position and final position. And then because the object can also move, right? So we also want to know, like, at what instant, what time instant is this object here, and at what time instant the object will be here, is here, right? So that's why at least when we talk about this situation here, at least we need two quantities or two variables in describing this object. So the first variable that we need here is the location of this object. And in terms of physics language, that would be called position. And the instant that we talk about the object's location, and that in terms of physics language would be called time. So that's why we need at least at the beginning two quantities, two variables, position and time. And I'm going to introduce some label here, some symbol here, excuse me. R here will represent the position, and time here, of course, is T. That's used in physics and also some other fields. We all use T to represent the time. Position, different people may use different symbols, but here we're going to use R here to represent position. But let's further think about in relation to our discussion of vectors. At least two quantities, vectors. So first, time here has no direction, right? It's just a quantity, a pure number. When we say today is December the 17th, then we just mean some pure number there, and there's no sense of direction whether it's to the right or to the left. So that's why the time here should be a scalar. Okay, so we're going to just do regular number addition or subtractions for the time, and then we don't need to worry about the vector property applying to the application to the time, because those are for the vectors. Now think about this position here. Position, you probably already realized that it's a vector, because let me draw something here. Let's say there's a two-dimensional motion, and there's a x and y axis, and here's the origin where we start to we used to measure an object's position relative to this O, the origin. And when I draw an arrow from the origin to this initial position, then I will have a sense of direction, both magnitude and direction, because this length here will represent how far away is this point to the origin. And at the same time, I also get the direction. Is along this direction with this angle. Let's call this theta I angle. And it's not other angle. Let's say I will draw a same length arrow going this way. Then they'll represent another position because the angle will be different, although they have the same distance to the origin. Right? So that's why the position should be a vector. So now let me use the vector notation. Let's put an arrow above this R so that we know it's a vector, and then we need to be careful when we do the operations on this vector. Now similarly, I can draw an arrow from the origin to the final position, and I can call this R final, and the previous one is R initial. Okay, so that's why location or position here is a vector. So we need at least these two quantities to represent this object's property, right, of the motion. And let me write down a composite quantity in a parenthesis, and this one is called Ri vector. So the first quantity here represents the position, and the second quantity is the time. That's R final, and then T final. Okay, so in the future, if you study relativity, you'll see that in Einstein's theory of relativity, space and time, they're intertwined. And whenever you talk about a space, you need to specify its time instant. So that's why we want to put them together and call this an event. So initial event is event I, and we have I and Ti to represent this event, and the final event is R final, T final. So now we have a complete description of the object's location, and also it's the time instant for that location. So we have complete information. However, it's not actually that complete, because people will also be interested in knowing how the object changes from initial to the final position. And then that will involve the subtractions of these two events. So we want to do event, the final event minus the initial event. So another question is, what is that value? All right, so since we already know how to represent an event, so how about let's put these two composite quantities into this equation. So we're going to do R final, T final, subtract R initial, T initial. So now what's the result here? So when we do this kind of subtraction, we want to associate the first quantity subtraction with the first quantity, and second quantity to the second quantity. Okay, so what we basically doing here is R final minus R initial, and T final minus T initial. Okay, so before we talk about the meaning of these two subtractions, let's just realize that that's what people do, right? So people want to understand how an object evolves from this initial position to the final position, and that would actually include the discussion of the evolution about the position and also the time instant, these two quantities together, and that makes sense, right? So in terms of future discussion, you will see the relation between them usually we have we will take a ratio between these two differences. We call that rate of change. So what property that we're talking about here by doing this subtraction is actually aiming at finding the rate of change, the time rate of change of some physical quantity, in this case the position. And we'll come back to this definition again later on. But now let's think about these two differences. So we do subtraction for the first part of the composite quantity, and then this quantity, the difference between the two positions, is called displacement. So we're going to call it delta R. So again, in physics and also in mathematics, whenever we talk about the difference, you call that delta, the Greek letter delta. The triangle here represents the difference of the two quantities, and it's called a displacement. Now you see it's also a vector, right? Because I have two vectors, subtraction, and then the result is a vector, as we discussed in the first chapter. Now here, the t final minus t initial is called delta t. Again, it's the amount of change of the time, and that is called time interval. The previous time here is called time instant because it refers to just one point, right, in time. But now it's the difference between two time points. Okay, so these are the several definitions that we need before we talk about the rate of change. Okay, so the rate of change of the of the position is called the velocity. So let's talk about the concept of the velocity. So we know first the delta R here, that's the displacement, R final minus R initial. Okay, and the time interval here is T final minus Ti. And then let me quickly draw the picture because we need to refer to this picture later on to talk about the direction. Okay, so here is the initial position, final position, okay, and then they correspond to Ti and T final. Now let me proceed further with this difference here. Since we know how to do subtractions for vectors, now let's see, R final minus Ri. That result can be obtained by drawing an arrow pointing from the head of this initial vector to the final vector, and that is R final minus R initial, or delta R. That is delta R. That's the displacement. So now the definition of the velocity is the ratio of delta R and delta T, and it's called the rate of change of position. Now let's see, we have delta R and delta T. That ratio is called the velocity, which is also a vector, right? Because I'm using a vector delta R here on the right side with a scalar quantity, and the result should be a vector. And also, by the way, delta T here is always positive. So that's always true. So that would mean the velocity here should have exactly the same direction as delta R, and its magnitude may change, right? Because delta T here will contribute to the change of the length of the arrow. But this velocity here It's not instantaneous velocity. It's not one instant. It's an average velocity. And the reason for that is because we're using a time interval, not one instant, right, to represent this displacement, the delta r. Okay, so now since we already know delta t is positive, so the average velocity selection is always parallel to delta r. So let me draw that in a picture. So that's V average. Now, how about the instantaneous? Instantaneous velocity. Okay, so that would be in the limit of delta t goes to 0. So that's the concept of the calculus, right? When we take the limit, when we have the limit concept, so something approaches 0, but it's not 0, which is small, really small, then that is called a limit. Right? Taking that limit, then we have this instantaneous velocity. So let's see. The symbol here will be just the V without the average. But now I'm going to say delta t goes to 0, and then delta r over delta t. So that limit is the instantaneous velocity. Okay, so now let's see. So let's say we take this limit for the 2 points already, then we should have a velocity for the initial position, right? And a velocity for the final position. Okay, so now that means that we have a more complete information. That's why I said that in the previous page, I said that the when I say R and T, I say complete image. I said for that time, yes, it's complete. But when we know more about this object's motion, we should add more information about its motion to this object's quantity set. So now the set of quantities that we need to describe this object's motion now is expanded to the following. So we're going to have, let's say, Ri, that's the initial position, and then initial velocity, we also know that, and then the initial instant, initial time. Okay, and then we have in the second set of information, we have R final, the position, the velocity, and then the instant. Okay, and then just like before, we need to study the evolution of this set of quantity to the other set of quantity. So how does the Ri change to R final? How does the velocity change to the final? Okay, so let's ask this question: how things evolve? How things evolve from this initial instant to the final instant. And then that will be our next topic. That's the acceleration definition. Okay, so now we know Ri, Vi, Ti, and then ask the question: R final, V final, T final. How do they evolve? And then that will give us this acceleration. So basically, the acceleration is the rate of change of velocity. Okay, so previously for v is the rate of change of the position, now it's the rate of change of velocity. And reflected in the mathematical language, it will be, we're going to calculate the difference here. So v final minus v initial, and we call it delta v. Okay, and similarly we still do this time difference, and then their ratio is the rate of change. It's called acceleration. And just like before, because this delta v, the change of the velocity, is in an amount of period, right? So it's in this time interval delta t. So that's why it's the average acceleration. All right, so now let's also draw a picture to represent this average velocity. Again, we need a Cartesian coordinate system x and y in a 2D motion. And then we have, let's say, we know the initial instant this object's velocity is vi. Okay, and then final velocity is v final. And then when we do delta v, we get this result. That's delta v. That's change of the velocity. And then that is parallel to the average acceleration direction. That's a average. Okay, but you may have a question, how do we get this vi? So previously I drew ri here, so now how come this becomes vi? Because vi and v final, they can be calculated using some other method. So we'll see that we can, from the positions diagram, we can actually get the velocity. We can draw that velocity. And that's why I can say I know this vi and v final already. We can talk about that, how to obtain vi and v final later on. Okay. And then again, the instantaneous acceleration is given by the limit delta t goes to 0. Then we have instantaneous a equals this limit delta v over delta t. Okay, so that is given by, in mathematics, is the derivative dv dt. Excuse me, I forgot to mention that in the previous page. So let's go back here, and that is called dr dt. Okay, and then again, we can do this further later on when we know the components. So let's see, r, remember, is in a 2D motion is xi hat plus y j hat. That's r, and I replace it by this component form. Now if I take a derivative of that, I can take the derivative independently for x and y component. So that's why we have dx dt I hat plus dy dt j hat. Okay, so now you probably I'm more familiar with this kind of notation, dx dt, because previously when I take a derivative of the vector here, you probably don't know what that means, but in fact it's very easy. It's just the two components of the vector, they will take the derivative independently. That's why we get these two terms. And dx dt is called vx. dy dt is called vy. Okay, so let me add the note here. So vx is dx dt, vy is dy dt. Okay, yeah, sorry about forgetting to talk about this meaning of the limit in the previous discussion. Now let's do this here. So now v here would be, in terms of component form, would be vx I hat, vy j hat, and then dt. Okay, and then we can do that independently. So we have dvx dt in the I hat direction, and then dvy dt in the j hat direction, and that is called ax. dvx dt is ax, and ay is dvy dt. Okay, so let's write this down. Ax is dvx dt. Ay is dvy dt. However, we can do this further because we already know vx is dx dt. So we're taking actually second derivative here with respect to the position vectors component x. So that's the second derivative of x with respect to the time. Now here similarly we have second derivative of the y component, right, with respect to the time. So now we have a more complete understanding of the object motion, because I also have this instantaneous acceleration for the initial and final instant. So let's write down this set of ever more complete information. For the initial time, I have position information, I have velocity information, I have acceleration information. Okay, now for the final time, I have final position, final velocity, and final acceleration. This information. Now you may ask, do we do this further? Like in the previous discussion, we already see the pattern, right? The rate of change will give us a second, the next quantity that we need. So do we need to discuss the evolution of AI to A final? Okay, so now for regular course, we don't actually need to do that. But if you're in some special field, such as auto industry, people need to study how the acceleration changes. With time, then they need to do this further, right? Further discussion of the rate of change of the A. And let me briefly discuss some quantities that we defined in that kind of special field when people need more information. So for example, the quantity jerk here, the symbol is J, is defined as the rate of change of the A, acceleration A. And then if you go to the next order, it's called a snap. The symbol is S, usually it's S. S is dj dt. And the next order will be crackle. The symbol is C, ds dt, the rate of change of the snap. And then the rate of change of the crackle is called a pop. dc dt. Okay, of course, the in the motion I'm going to discuss in our lecture videos here, we'll just stop here. We're satisfied with this kind of description. If you know already, like up to the acceleration of an object, then we say we have a complete information. Okay, all right, so that will be all for this video. Thanks for watching.